All right, welcome back. This is going to be for differential equations. Today we're going to cover why, when you get repeated roots, do you get the solutions you get. Okay, so for example, we're going to look at y double prime minus 4y prime plus 4y equals 0, right? So the first step here is to generate our characteristic polynomial. So we let y is equal to e to the rx. Okay, that's our first step. And then we're going to take a couple of derivatives. So y prime is equal to re to the rx. Okay, y double prime is equal to r squared e to the rx. Okay, so what we're going to have here when I put it back into my solution, we're going to have r squared e to the rx minus 4r e to the rx plus 4 e to the rx set equal to 0. We factor out the e to the rx from everybody. So we have e to the rx here. And what are we left with? We have r squared minus 4r plus 4 equals 0. Since e to the rx can never be 0, we're left with the other term. So we have r squared minus 4r plus 4 is equal to 0. You guys can factor this. This is going to be r minus 2 squared equals to 0. And then take the square root of both sides. We get r minus 2 equals plus or minus 0, just 0. So r is equal to 2. Okay, so one solution we're going to have y1 equals c e to the 2x. But wait, this is a second order differential equation. We should have two linearly independent solutions. So how do we get the second one? Okay, now normally you just slap an x on this and say, okay, well, we know the answer is going to be y2 equal to c1 e to the 2x plus c2 x e to the 2x. But why? Where does that come from? Okay, so it comes from reduction of order. That's what we're going to do now. So what we're going to do is we're going to presume, we're going to say, you know what? There's probably a second solution out here, y2. I don't know what it is, but we'll say it's some function times the first function, e to the 2x, such that y2 over y1 will not be a constant. Okay, so y2 is, even though it is y1 times a different function, that function is going to be something more complicated than just a constant. So it's not just a linear dependent form of the first solution. Okay, so what we're going to do now is we're going to take a couple of derivatives. We're going to say, oh, well, let's take the derivatives. So y2 tick is equal to, well, it's a product rule because these are two functions. We have derivative of the first times the second plus the first times the derivative of the second. That's going to be 2u e to the 2x. Okay. Now we've got a second order DE here, so we're going to say y double prime equals. So what's going to happen is we need to take the derivative of the first, so y double prime e to the 2x plus the first y tick, and then we have a 2e to the 2x here. Fix my space. Okay, so we're going to have plus 2. So we have derivative of the first times the second, so 2u tick e to the 2x. Okay, that's the derivative of this piece here. Plus, and now we need the derivative of this part. So we're going to say the derivative of the first, so u tick e to the 2x, plus the first times the derivative of the second. So it's going to be 2u e to the 2x. Okay, and then we're going to combine some terms here. Okay, at the end here we have our end here, which is going to be plus 4y. All right. So let's combine some terms. We have y double tick is equal to u double tick e to the 2x. Okay. We have a plus here, right? So we have how many u tick e to the 2x's? We have 2 plus 2. We have 4 u tick e to the 2x. It takes care of that one, and it takes care of that one. And at the end, we're going to have plus 2 times 2 would be 4u e to the 2x. Okay. Now let's plug back into our original equation. It's up here. Okay. That was back to y double tick minus 4y tick plus 4y equals 0. But in this case, our y is going to be our u times e to the 2x. Okay, so remember, our solution is y is equal to u e to the 2x. So we're just going to plug in what we found for our derivatives into these cases here. So we're going to have u double tick e to the 2x, okay, plus 4 u tick e to the 2x plus 4 u e to the 2x. And that takes care of my y double prime minus 4. What was u prime, or y prime rather? Okay, that was just going to be this guy up here. Okay, so we have 4, we have u tick e to the 2x plus 2u e to the 2x. Okay, so that takes care of this piece. And then we also have plus 4. Remember, our solution is u e to the 2x, because we're working this specific example. All right. Now we've got a little bit of algebra cleanup to work on. Right. We could do this more abstractly. I recommend that you do, but this is always going to work out this way. Okay, so we have u double tick e to the 2x plus 4 u tick e to the 2x plus 4u e to the 2x minus 4u tick e to the 2x minus 8u e to the 2x plus 4u e to the 2x. Now here, notice that a couple of things are going to cancel, right? So we're going to say, hey, this 4u to the 2x, 4u e to the 2x. There's a minus 1 and a plus 1 here. Okay. There's 4 plus 4 is 8 of them, minus 8 of them. Those are going to cancel. We have 4u tick e to the 2x, a minus 4u tick e to the 2x. What was the right-hand side of this formula? This equation started off as a homogeneous equation. So we have equals to 0, equals to 0. Okay, but all of this other business canceled. So we have u double tick e to the 2x equals 0. Well, again, we know that e to the 2x cannot possibly equal 0. So we are left with u double tick must be 0. Well, all we're going to do is integrate this thing. We're just going to integrate it twice. So we're going to say, well, we integrate. So we have u tick is equal to, I'm going to call it a for my constant for this case, and that'll just be a. And then we're going to integrate again. So we've got u is equal to ax plus b. All right. Now remember what my first equation was, right? We said y2 was equal to u times y1. So we've got ax plus b, and what was my y1 was c1, that was the constant, e to the 2x, right? So if you're not used to differential equations, there's a lot of abuse of constants that go on here. So a times c, a is a constant, c is a constant. We multiply them together, we get a constant. I'm just going to call a times c, c1, and then what do we have left? We have x e to the 2x, and then b times c1, I'm going to call c2 e to the 2x. So our two solutions here, y1 plus y2, okay, because remember that y2 is just going to be c1 e to the 2x, c1 plus c2, or call it a different constant if you'd like, but we're just going to get a constant e to the 2x For our other solution, we have a constant x e to the 2x. And that's why we get an x times our exponential solution to generate our second solution for our repeated root situation when we have second order differential equation with constant coefficients. Okay, so I hope that helped explain a little bit as to why we end up with this. By the way, you could repeat this for third derivatives, for fourth derivatives, etc. The algebra gets a little hairy, but what's going to happen is we can keep taking more and more integrals. We're just going to get bigger and bigger and bigger polynomials as we go through this. Okay, so thank you very much for tuning in, and I will see you in the next video. Bye.